Hello everyone, this is Nargis from Andrea University of Klagenfurt. I would like to present my dissertation with the title of The Scheduling of Data Flow Processing Applications on the Computing Continuum with the supervision of Radu and Hermann, mentorship of Dragi, thanks to my examiners Mihhail from KTH in Sweden, Andrea from Sapienza University of Rome in Italy, and Klaus as the chairman. I would like also to acknowledge the project, mainly the European Commission project, H2020 Data Cloud, Horizon Europe Graph Massivizer, and Austrian Research Promotion Agency based on projects such as Gaia and 5G Quarantine Fog. Firstly, I will introduce the main topic in this presentation regarding the application and computing continuum models, which leads to the presenting of the application scheduling problem, and then I will present the structure of the dissertation, mainly focusing on the research questions, objectives, and methods, such as, for example, the single-sided, three-objective application scheduling, double-sided synchronous application scheduling, and double-sided capacitive or asynchronous application scheduling, and then I will conclude this presentation. Modern data processing encompasses large amount of data that are collected from different sources, like the sensors or users' mobile devices that are going to be stored to be analyzed, which are quickly overwhelming the current cloud data centers. That's why the idea of computing continuum encompasses of the edge and fog computing as an extension of the cloud computing, firstly coined by Cisco, came into appearance. Cisco provided through its routers the functionality for the users to run some virtual machines managed mainly by open source softwares. Then later on, other cloud providers such as Exascale provided Exascale Edge resided in Klagenfurt, which we use also for our research works. Also later on, other cloud providers such as Google, or here in this case that you can see in the presentation, AWS provided wavelengths for ultra-low latency of 5G communication for mobile users. Then later on, also the local edge clusters, thanks to the projects, came to the universities, such as, for example, the case that I will present here. So maybe up to now you have also understood that we have two different perspectives. One perspective is the application provider having a large amount of data needs to be processed by different components or microservices or serverless components throughout the application, which need to be allocated to the other, like the other part, which are the resources in the computing continuum. So from one side, the producer of the data has some maybe large amount of data to be processed one by one through different data flows by the microservices. And then from the other side, there are these resources that the user wants to hire, rent, and then assign its task. Here, we need to explore actually the different requirements from both sides, like the application and resources. Going deeper into the application structure, let me explain about, for example, the text processing application here. So here sits the Amazon data scientist who has a large amount of data, which needs to be firstly retrieved from some data storage, decompresses, splits into, for example, training and testing part of data, applying some machine learning model for training the model, and then later on to use this trained model to score the test data, maybe also to have an update over the test data later on. So regularly this application microservices require some resources, maybe some updating also later on based on the monitoring data that regularly it will be collected. So these requirements are in terms of the processing and memory. As you can see, mainly, for example, for the training, larger number of CPU cores and amount of memory are required. From the other side, computing continuum, let's focus on the one that we use in our research also. Here we call it this Corinthian computing continuum, or C3, as you can observe also with the logo, which is showing the dragon. So it encompasses actually the AWS instance or the exascale instances located in different locations, such as Sofia in Bulgaria, Frankfurt in Germany, and Vienna and Klagenfurt in Austria. Also, they are interconnected to some single board computers such as Pi and NVIDIA Jetson Nano devices. For further information, I would like to attract your attention for the general information presented in this paper and later on to the C3H paper, which presents how to create an automated Mininet compatible testbed over the Pi and Nano devices. In this dissertation, I modeled the computing continuum as a finite set of devices which have a specific capacity in terms of the processing and memory and storage. And then later on, I modeled also the network communication or network channeling between them based on the latency and bandwidth capacity of each one of these networks. The main research problem explored in my dissertation was the application scheduling. So where exactly to run each one of these microservices, and even in one method I explore at which time to start the execution and then at which time to release it so that it will be allocated later on to other microservices. Thanks to the orchestrator platform, such as, for example, in this case that you can see in the slide, the Kubernetes developed and maintained by Google, so that it provides a functionality for the application provider to submit one's application through some APIs to the orchestrator platform to be executed on the computing continuum that previously had joined the computing infrastructure. Here, by default, this orchestrator supports some scheduling. So I applied my own scheduling algorithm based on the objectives that wanted to be optimized. And then later on, the decision was taken where exactly to run each one of these applications. Later on, I will show you through different methods how it was achieved. So the main structure of my dissertation goes to mainly from top to bottom, considering two different synchronous execution models for the data flow processing application. The first and second method are based upon the synchronous execution model. The objective one explores minimizing the time, cost, and energy, while the objective two explore minimization of the data processing and transmission time, and then the maximizing the residual bandwidth. Shifting from objective 1 to 2, or the method 1 to 2, was based on supporting both the application and resource provider's perspective, while just MAPO, the first method, explores the application side. Then I also explored the asynchronous execution model in the last method, which was based upon supporting both, the application and resource provider, and also the asynchronous execution model. The first research question goes to which optimized scheduling and resource allocation model can improve the energy and cost from the application provider side. The second question explores the algorithm that one can apply to allocate the application microservices to the computing devices from, as I said, the application and resource provider's perspective. As you can observe, transmission and processing times, along with the residual bandwidth, were the main target and aim of this question. So the question 3 explores how to model a queuing-based, non-blocking type of communication between the microservices to improve the processing, queuing, transmission times, of an asynchronous application execution. The three different methods are listed here, as you can observe, mainly exploring the scheduling from the perspective of single site or double site, or even double site capacity aware, by following the research work that have been published in different venues. The main experimental design are based upon the metrics that I have evaluated, the methods for that, like the application completion time or the microservice data processing queuing time, transmission time of data, the energy consumption cost, data transfer intensity, and all of them were evaluated through the testbed design. One of them the simulation, and the other one to the real testbed, so that we run the real application over the real testbed. The first method, under the name of MAPO, explores how to minimize the time, cost, and energy. While the state-of-the-art method were mostly focusing on the weighted objectives, or sometimes a single objective or a bi-objective, here we targeted the three-objective optimization. And the algorithm decides based on the NSGA2 model, which are the main scheduling solutions that are non-dominated at the end, and then the decision-making component of the architecture based on the preference of the user decides over the scheduling for each one of these microservices of the application. Talking about the microservices, let's assume that there are three different, as shown in this slide. They are interdependent to one another, and then they are going to send some data in between each other. So, for example, the upstage microservice determine mental health state sends multiple data elements, but how they are being communicated. So in this case, Mental Health Act blocks all the data elements of the data flow until all of them are one by one received. So here we applied something like a data synchronization barrier. And then the same happens here in between the Mental Health Act and find the closest clinic. Then, based upon this communication in between the microservices, it was required, based on the MAPO scheduling, how to allocate the resource and schedule the application components like the microservices over the computing infrastructure. Mainly, the application that you can observe here is the mental health application, which is an IoT-based application, and it is used in the several UK-based hospitals. The main model is based upon the multi-objective optimization. So it searches for a set of non-dominated schedules of the microservices on the devices, starting from the nadir point. For example, as you can observe in this figure, I just showed two objectives, although the main algorithm is based upon the three objectives. So this point has the worst completion time, the worst theoretic completion time and economic cost. And as we get further from this point, so that the scheduled solutions which are on this frontier are better than the nadir point, and then as we get to this ideal point, which has the zero time, zero cost, then the solution get better. However, as you can observe, here is the frontier, which has which consists of the almost optimal solutions, and this type of solutions are non-dominated to one another, and it's based upon the user requirement, here called the decision-making algorithm a priori, which solution to be considered. For example, here with the lowest time, or no, here with the lowest cost. The evaluation shows that MAPO selects the devices with the lower completion time while achieving a trade-off in between the energy and cost compared to the FSPP, or first service placement problem. In the other scenario, which was the data element size. So increasing the data element size increases the time, energy, and cost, while map improves the energy and time in this case. However, the cost is, in comparison to FSPP, is not improved because FSPP mainly targets the cloud-based resources or instances or virtual machines, which in the experimental design we considered lower cost for the cloud instances, while higher costs were for the edge, which are in the vicinity of the users. So getting closer to the next method explores a double-sided synchronous application scheduling, which both from the resource and application side. So here we need two different ranking methods. The first ranking method explores the minimization of the data processing and transmission, while the second method explores the residual bandwidth, maximizing the residual bandwidth. So the way that we approach to solve the problem was based on a game. We assume a game between the microservices on one side interconnected through a structure of a directed acyclic graph to be played with the devices on the other side interconnected throughout the the computing infrastructure. The microservices rank the devices on the other side based on the processing time and transmission, while the devices rank the microservices based on the residual bandwidth. Lower residual bandwidth has a really higher rank, while highest rank, and then the better the rank is, so that it shows that it has the highest bandwidth remained for that specific device. I mean the downlink bandwidth. So as an example, here you can observe that M0 has ranked device, the microservice 0 until microservice 4 have previously ranked the devices, the computing devices, and M0 has ranked D0 with the highest rank, and also M2 has ranked D0 with the highest rank. On the other side, D0 as a device in the computing continuum has ranked M2 and M0 with the highest rank. Therefore, as you can observe in the final matching, D0 has been matched to M2 and M0 because it has enough capacity to host both of them. While the other microservices, for example, such as here, M4 has been matched to D3 because D0 does not have enough capacity for its other ranked microservices. To evaluate this method, I designed the video processing application, encompasses of the transcoding microservice, framing microservice, high accuracy training, and inference of the object in the frame consisting of the traffic sign. The evaluation shows that CODA, which is the name of this method, has a better, reduces the completion time in comparison to the other state-of-the-art method. However, in terms of the data transfer intensity, in comparison to RTR-RP method, it does not improve the data transfer intensity, mainly because CODA puts or places or schedules the microservices over the transcoding microservice over the edge resources, which really put a lot of load on the network channels in this case. The next method explores a double-sided capacity over asynchronous application schedule. It minimizes the processing and queuing time, and while minimizing the transmission time as well. As you can see, a modification was applied to the architecture in comparison to the previous method proposed, that the game is applied multiple times based on the number of dependency level that we have identified in the DAG of the application. Moreover, the execution model of the application is based on the asynchronous, which I explained through the following slides. So, assuming there are two different microservices retrieved, split, and vectorized, Then one microservice sends the data elements to the other microservice. There is something like a queue that temporarily stores the data elements while there are some processing applied over the other data elements. So this helps to have some data elements temporarily stored while there are some processing queue almost. So in order to model this queue, we have 6 terms to be defined. One of them, the first and second term, are based upon the interarrival and processing distribution, which in this case is M showing the exponential interarrival time and processing in between the data elements. Each queue is going to be assigned to one microservice, and then the strategy for first come first serve for the entrance and exiting of the data elements from the queue is followed. The batch size shows the number of elements in the queue, and then the size shows the whole number of data elements in the data flow. Also here we applied the game, but as I said, we have applied multiple games based on the number of interdependency level in the application structure. The game is based upon the microservices rank the devices based on the processing and queuing time, while the devices rank the microservices based on the transmission time. Then the utility function is aimed to be maximized, which shows the profit of both sides of the game, like the microservices and devices. Here, as an example, let me explain about the structure or the DAG that we have considered. So here, from the source to the sink, there are 2 different data flows, though there are 3 different levels. The first level consists of M0 and M1 microservice, while the second level of the application or data flow processing application encompasses the M2 and M3. The last level encompasses M4. From the other side, the computing continuum consists of 4 devices. So in the first game, M0 had rank D0, while M1 has rank D3. So both of them are going to be matched to the devices, as you can observe, because they have enough capacity to accommodate them, and also they have previously ranked these microservices. In the other game, M2 and M3 look into their preference list and see, for example, D0 is being ranked, and then M3 sees that D3 is being ranked. Also, D3 has ranked M3, and also D0 has ranked M3. That's why, while they have enough capacity, based on some monitoring data that we really through the implementation and modeling we understand, then these 2 will be matched to their preferred choices. How about the last microservice in the last dependency level of this DAG, which is M4? M4 is going to be matched to D3. Is it really? But D3 does not have enough capacity. So that's why they try to remove one another from their preference list so that they help to reach a stable game, as you can see in this slide. Therefore, therefore M4 will be proposing to D1 if D1 has previously ranked M4. It seems that it has been ranked, therefore these 2 will be matched to one another, and then at the end we reach to a stable game, which none of these players prefer to be matched to one another. So in order to evaluate this method, we designed 2 different applications. One of them is the video-based, queuing-based, the video processing application for road sign inspection, and the other one for text processing, mainly for sentiment analysis or extracting the sentiment of the customers of Amazon products based on their reviews. To evaluate the performance, we had 4 different metrics, like the element queuing time as well, and we designed 2 different scenarios. One of them, the processing load analysis with different number of producers of the application required, one replica of the application, the other one data flow analysis based on the different number of batch sizes or the number of elements in the queue before processing. The evaluation shows that Though the completion time of the application based upon the decision making of C3 match is improved, but the transmission time is not that much improved because of the distribution of the microservices over the whole continuum. That is the main strategy of C3 match in comparison to the other methods like the CLIP or KCSS, which mainly collocate the application over, for example, the fog devices. Though we have, not improved transmission time, but in overall, the completion time of the application was improved. In the other scenario, which is data flow analysis, we had two applications, and mainly the training microservices of both of these applications, like the roadside inspection and sentiment analysis for text processing, were among the microservices that had the higher queuing time. As a conclusion, I would like to present the three contributions of my dissertation. For the first method, we had lower completion time, although a trade-off between the energy and cost, while, for example, in the data element size scenario, we had a lower energy consumption, and the other scenario, which was the CPU workload, we had a lower cost. In the other contribution, we had a lower completion time, while the data transfer intensity was improved, was lower than the two state-of-the-art methods. And the contribution 2 focuses on double-sided capacity-aware asynchronous application scheduling, mainly targeting and having a lower data processing and queuing time, and in the data flow analysis scenario, lowering the data transmission time. Thank you, everyone.